In the early 1900s, industry chased a simple promise: make metal last. Chemists worked with chromium compounds that behaved in a special way, forming coatings that resisted rust and wear. Hexavalent chromium stood out. It delivered sharp, reliable results, and it did it fast. Factories noticed. So did manufacturers who needed dependable finishes on tools, pipes, and machinery. A chemical that looked like progress started to look like a necessity. Chromium 66 also brought colour. In an era hungry for modern materials, its pigments produced bright yellows, oranges, and greens that held up under heat and sunlight. Paint makers, printers, and metal finishers leaned in. The value felt obvious: better protection, stronger products, cleaner-looking surfaces. Orders grew, production expanded, and processes left the controlled world of the lab. The compound became something people handled daily, not just something scientists studied. As demand climbed, hexavalent chromium moved through more hands and more places. It travelled in powders, solutions, and slurries. It ended up on factory floors, in rinse tanks, and on parts shipped across the country. At the time, the focus stayed on performance, not exposure. The same features that made it useful also made contact hard to avoid once it scaled. The stage was set for widespread human and environmental interaction. Chromium 66 production grew fast, and it spread into the places that kept modern industry running. Plating shops used it to coat parts. Pigment plants used it to lock in bright, durable colour. Tanneries used it to process leather at scale. More output meant more handling, more dust, more mist. Workers stayed close to it for hours, day after day. And then small injuries started showing up that did not heal like normal. The first signs looked ordinary until they kept repeating. Skin ulcers appeared on hands and forearms where splashes landed. Noses bled during shifts and crusted over afterward. Some workers lost their sense of smell. Others developed a rough, persistent cough that did not match a cold. People blamed heat, acids, or bad ventilation. But the same set of problems kept clustering in the same kinds of jobs, where chromium V was used and breathed in. As more shops and plants ran chromium V processes, the pattern became harder to ignore. New hires developed the same symptoms as older hands. Different towns, similar complaints, similar timelines. Illness stopped looking like bad luck and started looking like exposure. The chemical that protected metal and coloured products also burned tissue and irritated lungs when it got inside the body. In these workplaces, occupational disease became visible, linked to chromium VI by repetition and proximity. By the 1930s, the complaints from the shop floor started to match what doctors saw in clinics. Workers who spent years around chromate dust and mist did not just get sores and nosebleeds. Many developed lasting coughs, shortness of breath, and damaged airways that never fully recovered. Case reports and hospital notes began to pile up. The pattern looked less like irritation and more like long-term injury. Then a more alarming signal appeared in the record. Factory medical files and published studies increasingly linked heavy chromate exposure to higher rates of lung cancer, especially in jobs where breathing the material was unavoidable. The risk did not show up overnight. It rose after years. That delay made it easy to ignore at first, but harder to deny once enough workers reached the same outcome. Even as that evidence spread, production kept climbing because the chemistry kept paying off. Chromium VI still protected metal, fixed dyes, and supported fast-growing manufacturing. But the language around it changed. In scientific papers and in early regulatory discussions, it no longer sounded like a helpful industrial tool. It sounded like a carcinogenic hazard that demanded limits, controls, and warnings whether industry was ready or not. After the war, the economy surged in a very specific way. It rebuilt. Highways stretched out, bridges multiplied, power systems expanded, and new factories fed a consumer boom. All of it depended on metal lasting longer in rain, salt, and exhaust. Chromatic primers and corrosion inhibitors fit that need. They got brushed, sprayed, and mixed into routine production. Chromium VI stopped being a specialty chemical and became a default step. At the same time, aerospace grew fast and it demanded materials that stayed strong while staying light. Aluminum parts still corroded, fasteners still seized, fuel systems still degraded. Chromate coatings and electroplating answered those problems with reliable performance. That reliability mattered more than inconvenience or danger. So suppliers scaled up, then scaled up again. More plating lines ran, more drums shipped, more workers handled solutions that contained chromium VI. The big change was not one new product, it was the web. Chromium VI travelled through national supply chains, from chemical producers to primer makers to plating shops to manufacturers to maintenance depots. It reached shipyards, rail shops, construction contractors and small subcontractors that never called themselves chemical companies. The number of hands and sites multiplied. Exposure risk spread with the business model. The chemical got built into everyday industry. Factories produced mountains of leftover liquids and sludge, and much of it went to the cheapest place possible. Wastewater sat in unlined ponds, where nothing blocked it from soaking downward. Pipes and trenches carried spent solutions across a site, and when they cracked, they leaked quietly. Some waste got dumped straight into soil, treated like it would stay put. It did not. The ground became a slow conveyor belt. Hexavalent chromium moved with water. Rain and runoff pushed it through loose fill, sand and gravel, and it followed the same paths that fed wells. It spread beyond fence lines, not in a dramatic spill, but in a steady seep. The troubling part was timing. It took years to reach an aquifer, and once it arrived, it kept travelling. By then, the original disposal had looked like ancient history. That shift changed who got exposed. At first, risk had seemed locked inside workplaces, on the shop floor, at the tanks, in the air. Groundwater broke that boundary. A contaminated plume turned ordinary routines into contact, drinking, cooking, making infant formula, filling a glass from the tap. There was no smell that warned people away. The harm moved from employees to neighbours, then to whole towns, one well at a time. In the 1970s, a new set of environmental laws pushed pollution out of the shadows. States and federal agencies started requiring permits, record-keeping and water testing in places that once operated with little oversight. When groundwater monitoring wells went in near factories and waste sites, the results landed hard. Chromium VI showed up where it was not supposed to be, moving underground, spreading beyond property lines and reaching the same aquifers that supplied nearby drinking wells. For the first time, contamination was mapped instead of guessed. Investigators traced long, thin plumes of polluted groundwater that pointed back toward plating shops, pigment plants, and disposal areas. But the new system also exposed a problem. Standards did not match from one place to the next. Some agencies treated chromium VI as an urgent hazard. Others focused on total chromium, or set higher limits, or delayed action while more data was gathered. The science moved faster than the rules. Cleanup sounded straightforward, but it rarely moved quickly. Pump and treat systems took years to design and longer to show results, and many responsible parties argued over costs or questioned how far the plume had really travelled. Meanwhile, residents depended on the same wells while decisions crawled through paperwork. By the 1980s, chromium VI groundwater pollution no longer looked like an accidental byproduct. It looked like a regulatory problem, documented, measured, and still left in the ground. In the 1990s, hexavalent chromium stopped being a problem buried in lab reports and agency files. It entered living rooms. A few community contamination cases rose above the noise, and one became the name people remembered: Hinckley, California, a small desert town linked to Pacific Gas and Electric, or PG&E. Residents reported health worries, and the question shifted fast from what was in the water to who knew and when. Lawsuits changed the balance of power. In a courtroom, contamination did not stay abstract. Paper trails mattered. Expert testimony mattered. So did the personal stories of families who believed their drinking water had been compromised. Hinckley put a specific chemical name on national tongues, and it put a corporate logo beside it. The case framed hexavalent chromium as an accountability issue, not just an environmental measurement. The ripple effect went far beyond one town. Other communities looked at their own wells and asked the same blunt question: was this happening here too? Regulators faced louder pressure, companies faced higher legal risk, and chromium VI became a public symbol of industrial harm. The fight over parts per billion turned into a fight over trust. In the 1990s, hexavalent chromium became a cultural and legal flashpoint. Through the 2000s, the fight shifted from discovery to definition. Everyone asked the same question and got different answers. How much chromium in drinking water was actually safe? Agencies rechecked old assumptions and the numbers moved. Some limits focused on total chromium, not the more toxic form. Communities heard that change and felt whiplash. A standard was not just a line on paper anymore. It decided urgency. Underneath those numbers sat a deeper argument about method. Toxicologists debated which studies counted, which health effects mattered most, and how to estimate risk from small, long-term doses. Regulators weighed animal data against human evidence, and each choice shifted the final limit. Industry pushed back, warning that ultra-low standards demanded expensive treatment everywhere. Public health advocates insisted the opposite, that waiting for perfect proof meant accepting preventable harm. The science became a battlefield. Then came the question no formula solved. Who paid? If chromium VI in a well traced back to a plant that closed decades earlier, responsibility became a legal maze. Utilities argued they did not create the pollution, but still had to deliver safe water. Companies fought cleanup orders or negotiated slower timelines. Towns demanded filtration, bottled water, and medical attention, not studies. In the end, governance meant conflict over standards, over evidence, and over accountability. In the 2010s, the pressure finally changed what many companies actually did. In more factories, chromium VI stopped being the default choice. Some switched to different coatings and pigments. Others redesigned processes so less chromate ever left the line. Controls tightened too. Better containment, better wastewater handling, more checks. But progress came in patches. The places that moved fastest looked cleaner on paper, yet the old damage stayed put. Because the biggest problem no longer came from fresh dumping. It came from what had already soaked into the ground years earlier. Those underground plumes did not disappear on a schedule, and they did not respect property lines. Cleanup turned into a long campaign. Track the contamination, pump and treat water, and stop it from spreading. The work sounded straightforward until costs rose and timelines stretched into decades. One fix aimed straight at the chemistry. If chromium VIX could be reduced into chromium-3, it became far less mobile and far less toxic. Some sites used chemicals in the ground to force that change. Others tried mixing, injection wells, or reactive barriers. Results varied. Local geology mattered, oversight and funding mattered, and while some plumes shrank, many remained stubborn. The era became cleanup and replacement, yet contamination persisted. By the present day, hexavalent chromium sat in a different category entirely. Regulators treated it as a serious hazard, not a helpful industrial ingredient. Permits tightened, reporting expanded, and water systems faced closer scrutiny. But rules did not erase what already reached the ground. In towns near old plating shops, military facilities, and industrial yards, contamination remained in place, moving slowly through aquifers long after releases stopped. For residents, the modern routine became measurement. Wells got sampled again and again, sometimes for years, because levels shifted with seasons and pumping. Where tap water drew from affected sources, utilities added treatment or blended supplies to drive numbers down. Homes relied on certified filters, cartridges, maintenance schedules, and lab results pinned to fridge doors. The danger felt less dramatic than an accident. It lasted because it stayed embedded in water people needed every day. Cleanup moved on a separate clock. Companies and agencies drilled monitoring networks, mapped plumes, and ran systems meant to pull water out, treat it, and send it back or dispose of it safely. Some projects reduced chromium VI to chromium-3, then tried to lock it in place. But geology and funding dictated the pace. The result felt like progress and unfinished business at once. The chemical once praised as a cure still demanded decades of repair.